Hello. 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 I think it's already been 8 minutes. I think I'll start the class. If anybody wants to listen, you can listen to the recordings. So, otherwise, I will wait for 2 more minutes. We'll see if anybody can join. Mm. Okay, fine. I will start the class. If anybody wants to listen, you can retape the video in the later days. So, I think I'm going to share the screen. Assuming that my screen is visible. So, in today's class, yeah, yes. So basically, till the last class, till week 8, we have gone through the classical thermodynamics. For the last 4 weeks, we will go through the statistical thermodynamics. So if you remember, this is the one of the first slide which I have shown you in the initial days to differentiate the classical thermodynamics. If you remember, we have done the classical thermodynamics for the microscopic approach, classical for the microscopic, and we have studied the extensive and intensive properties. If you remember it, and say suppose in the classical thermodynamics, we will consider a matter as in a whole. Say suppose we have the one formula Cp minus Cv equal to Tv beta square by K. This formula is valid for if you take any solids, liquids or gases. Okay, the formulas which we derived through the classical thermodynamics, they all talks about in the bulk. Say suppose we have an isolated system, and you have an isolated system, and you have certain volume and certain pressure and certain number of molecules, and then what is the approach to be done. So but the major missing part is if you take any pressure, if you take any pressure and temperature, there will be Avogadro number of molecules will be there in that particular given system, and this will be the further we will discuss it. So there will be Avogadro number of molecules, and there will be interaction between these molecules, and that parts will not be covered in the classical thermodynamics, because as initially we have discussed that classical thermodynamics will take all the entity as a single ball particle. Say suppose if you remember the van der Waals also, there they have taken, if you remember the V minus B or A by V square, here if you remember there is a formula of RT by V. So if you remember V minus B, where what we have done was we have taken all molecules as single entities, and we have not considered the molecular interaction between these two or the repulsion between the forces with these two. Okay, so that all we all eliminated, and we have done the what is mean by pressure or volume. We calculated through these formulas, even the Redlich equation or the Redlich series equations. Whatever we have done, we have taken all the molecular entity. We have never carried out the relationship between the two molecules, and how the intramolecular force of interaction will be attraction will be there between these two molecules, or between along on this one itself. So that all will be term in type of microscopic approach. Say suppose as a basic example which the sir has discussed was, if you have the protein ligand system, we will get the protein ligand. So once you have the protein ligand system, what you will do was, say suppose there will be some if I ask you to find the delta U, which is minus Q minus W, this is from the first law of thermodynamics. So if I ask you to find out the delta G, which is nothing but which we know is delta H minus T delta S. So now if we come to delta H, we know it as delta U plus P delta V. So now how the internal energy is calculated was, so we know that we can get the, if I have given the system and if I ask to find out everything, we can understand, but here we have the two properties and we need to understand the interaction between these two properties. So then what we will consider was delta U is as delta Uij, it's of ith of protein, ith atom of protein reacts with jth atom of ligand. So from this, even the small intermolecular interactions and intramolecular interactions were carried out to give the final value of delta G. So this is not only the final case. So where does the microscopic approach will be used? So I can give you some better examples. Say suppose this is one of the cases where you have the box and you have the protein, and there is a ligand, and you need to understand the how better it is binding affinity. So this is one example, and another example of my research is, say suppose you have the box, I mean not the box, say suppose you have taken the one small box where you have kept the lipid bilayer. Say assume if you have taken any chemotherapy drugs, how these drugs were, if it is going through the IV, how these drugs were can be penetrate through this model. So how it can be penetrate through this, suppose the chemotherapy drug has been given, how this drug can be gone into the nucleus. So what we can study here was we can study the penetration of the drugs through the lipid bilayer. So I'm telling in the biological perspective. So here we will use the bias potentials. So because we are pulling the drug from one end to another end, so here we will use the bias potential. So by using the basics of Boltzmann distribution law, by using basics of Boltzmann distribution law, or there is a term of RDF, which is nothing but a radial distribution function. Say suppose what it will do was, say suppose you have the box and you have the two components. Say suppose if I am taking CO, not CO2 plus say suppose water molecules. Say suppose the CO2 goes like this. So now what I want to find out was, if I want to calculate the RDF, what I want to find out was O of CO2 of H of water. So what I'm saying was, there is one, we are taking O1. Say suppose the CO. So O1 of CO2, which is related with H1 of water. So now what I want to find out was, in the given system, so if this is the system, and if there is suppose oxygen O1, 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 I'm just writing it. So this O1 we will make one circles of RDF. So we will understand that how many water H1 is closer to this O. We will get one graph, and how many O's. So this is for the OH. This will be for the HH of water. I mean, say suppose the H1 is related to how many H2. So suppose it's like this. This is H, and this is the H1, and this will be H2, and there will be another H2. This will be another box. Don't need to worry. There are the PVC condition will be there. So you can see if I make the plots regarding here. So what does it say was, we can understand the molecules which are very, say suppose if you have the bulk systems, and we can understand that okay, which molecule is providing the better force to over this one. Say suppose even for the van der Waals also, say there are different types of molecules. We are not calculating. See, in the van der Waals we are use the V minus B, but here if you take it, we can do the intermolecular attraction and say that if we calculate the RDF, we can understand that which molecules are nearer, and then we can apply the LJ potential to understand that molecular interaction and everything. From here you will get the partition function. Once you know the partition function, you know how to get the pressure. That was discussed in the class by sir, and we'll come to that part in the second half, I mean later part. So there are different examples we need to use to understand the microscope. So suppose, to put it in simple words, classical deals with the macro, where macro consists of huge number of microparticles. On these microparticles, information can be getted by statistical thermodynamics. I think my voice is clear, right? I just want to see.
Yes, sir.
Yeah. I think. Hi, Ishwajit, you are a new student?
Yes, sir.
Okay, fine. I mean, I didn't see you from the last three classes. I mean, last classes, so that's why. Okay, fine. You can see the screen, right? I thought no one has joined the class.
Yes, sir.
Okay, fine.
It is visible.
So you joined now, or like you are there from the starting? Because I can explain you like this basic examples again.
Sir, I have watched previous recordings, so
Okay,
yeah.
fine. No issues. Yeah, fine. So what I want to say it was, so I'm just saying the transition of how we can go from classical thermodynamics to statistical thermodynamics. That's what I want to give the major headlines for this class. So this is also in classical we will discuss more of the micro. In statistical we will discuss of more of micro, and this micro will, if you accumulate all the micro details, which will become as a micro. So this way you can regenerate, or I mean you can give the much more details of the system information to that. Say suppose as initially I have said that if you ask to delta G, if you are calculating the protein ligand interactions, we will say MMPBAC or anything. For their binding energy we will use this formula, but we can't calculate the enthalpy, so we will calculate this as delta U plus P delta V. So this we will get it through the microparticles. Say suppose, so if the protein has say suppose 100 amino acids, and each amino acid has like say suppose 6 atoms, and this each atom will goes with the one atom of ligand, and this all are one microparticles will accumulate to give to the information of delta U, and then we will get the delta G. So that's what, if you see the delta G formula also, it will be of so we will have the more interaction of together, so that's why the value will always be delta G will be negative. Okay, these are the basic examples of what we can do with the statistical thermodynamics. If I comes to the statistical, from the term we can coin, there will be more of mathematics and probability. Of one of the segment is probability. So to study the microscopic particles, I'm just giving the one line of theory. Microparticles, study on the microparticles. Initially they started with the classical mechanics. Then they come to the quantum theory, which converted to the quantum mechanics. Which is then converted to the statistical mechanics. From there they use the statistical mechanics to understand the statistical thermodynamics. So classical mechanics means you will have the Newtonian motions, where easily you can say from here you can easily understood the, if you take any full body, if I take any mass of the body and it is moving, for this you can calculate the position and the coordinates together, I mean position and velocity. So velocity is nothing but dv by dt. From the acceleration you will get a equal to dv by dt, and for position you will get dv by dt. Sorry, 1 second. So v equal to dp by dt. Displacement is nothing but a displacement. I have written dp for the understanding of position. So if you use the Newtonian motion for any microscopic body, you can easily find out the position. Say suppose if I given that body is moving with f equal to ma velocity, you have seen it from the basic classes, v equal to u plus at. From here you will get the velocity, and if I do dp by dt equal to v, which stands for dp by dt equal to v, which gives rise to u plus at, which is nothing but dp equal to v of dt plus at dt. If I do the integration, you will get the positions as vt plus of at square. So it is in x direction, y direction, and z direction with constant c. Okay, so these are the from the Newtonian motion. So once classical mechanics failed to explain the black body radiation, so it starts to give the results in the false way of saying that okay, the radiation will increase going on, but it's not the case. So then the Planck has designed the quantum theory. From the Planck, the Bohr and the Einstein all as used for the photoelectric effect. And from here they generated the quantum theory to quantum mechanics. From there the Schrodinger has used the wave function. Schrodinger uses the wave function by considering the particles considering the particles in the wave function. So where he have taken the coordinates and the time, and then he derived the wave functions. I will give that theory in the later part. If you go into the studies, wherever it is necessary, I will explain you that part. For now, if you remember in the class, sir has mentioned the formula of, one second, the partition function equal to, there is one formula, q equal to 8 pi mem a square by h square k. So this is gets from the Schrodinger equation, because the Schrodinger equation basically arises from the Heisenberg uncertainty principle, which says we can't calculate the simultaneously. It will be very difficult to calculate the momentum and the velocity, momentum and the position, velocity and the position of the system. So from there he converted this to the Schrodinger function, and then we obtained the value. So this is the basic outline of how we can use the quantum mechanics, and I will deliberately use examples whenever it is necessary. So first we will go to the statistical mechanics. Say suppose we have different states, and in the Schrodinger equation he defined everything with the potential energy of the function. So it means whenever we are talking about the positions, we will talk about the energy states. So that's why from the starting of the class, sir used to do with the epsilon and E, total energy. So because the Schrodinger has been, the Schrodinger equations has been derived based upon the potential energy of the function. So energy of the function at this position. So that's why we are using the energy states. Here the states are energy states, if you need to remember it. So if you remember in the first class, sir has gone through the distribution of 4 particles in 2 energy states. So what does it means was, so they have the 2 different states. So one is at, say suppose one is at x, one is at y. So 2 different states, and you want to ask the 4 particles we need to divide. Say suppose this can be done the random way. So total we have 5 microstates. So just assume it is like a mathematics problem. We have like 2 different states. Okay, 2 different states, and how many we can fill it. So total there will be 5 macro states of filling it. Now here we are not considering that which molecule it is, because say suppose we consider that all molecules are same, but what if the molecules are distinguishable? Then we have for each state, say suppose if I consider this state, we have 3 molecules, x, y, z, w, 4 molecules. So now I'm taking the probability. Say suppose we have the 2, 2 configuration. So for this, how many microstates we can attain? You need to remember, whenever we are talking about the microstates, we are talking about the molecules in the system. Okay, so if I talking about the macro, it is in general. So suppose we have 2 states, like a state variables. We have state 1 and state 2, and what will be the energies there. In the same way here also, we have 2 states, which in the terms of energy states here, one is at down and one is at the top. That is called a macro state. But when I am talking about the molecules, we need to talk in the terms of microstates. So now here we can if I take 2 2, either it can be xy zw, or it can be xy zw, xz yw. So there are how many will be there? There will be 6 will be there. So next thing, anything. xy yz xy zw xz xw yz yw. I think I covered all, so it will be xw. So there are total 6 microstates. Okay, you can calculate this in different form also. So you have 2 states and you have 4 molecules. So how many combinations you can get was 4c2. It means 4 factorial by 2 factorial into 2 factorial. So you will get the 6 microstates. If we do another example, say suppose if I say suppose you have 5 molecules and you need to fill it in say suppose 2 energy states of configuration 2 comma 2 sorry 3 comma 2. So 5 molecules and you need to fill it in the 2 energy states of 3 comma 2. So how many micro states you can get? So we have taken one macro state. So macro state means we are assuming that there are 3 molecules here and 2 molecules there, and if we come to how many micro states we can fill was same again. You need to do the combinations you can try. So first initially you want to fit the 3, so 5 C3, and then whatever the remaining 2 it will go here 2 C2. So now it will be 5 factorial by 3 factorial into 2 factorial. So yeah, it is this one. You don't need this one. Into this will become as 1. So this will be 5 into 4 by 2. So you will get 10 microstates. You can try this example. You can take 5 molecules A, B, C, D, E, and try to fit it in like a 3 on the top. I mean 3-2 configuration. You understand that 3-2 configuration means 3 will be on the top, 2 will be on the down, or 2 will be on the up, 3 will be on the down. Sorry, yeah. No, this will be the configuration. This is the 0, sorry. This will be the configuration because we are talking 0 state and first state. It will be 3 and 2. So just try to find out that how many configurations we can try. I can say ABC, ADE, ABD. Understand, right? The 3-2 configuration is in the down state there are 3 molecules. In the upstate you have 2 molecules. So you can find out that how many microstates we can get. So if you do the combinations directly, you will understand that you will get 10 microstates. So this is how can you find out? I mean, if somebody asks that, okay, I am giving you microstate, and how many microstates are possible, and this is one of the way to do it. And there is another type of problem. Instead of saying that to distribute this into the how to say it, 2 energy states, they will give the total energy. See, suppose as sir explained in the class, 4 particles system with the total energy of 5E. So now what is yours? This is the initial 1E, 2E, 3E, 4E, 5E. Now we have 4 particles and you need to fix it. Say I can say suppose first case I will put, again it is also probability cases only. So I will put here 3 molecules, 1 molecule here. So I think I am making sense. So 0th case, sorry, 0, 1, 2, 3, 4. So 0, 1, 2, 3, 4, 5. So first case what I will do was, this is the first case. So I will keep 3 molecules here and 1 molecule here. In the second case, I will keep 1 molecule here, 1 molecule here, and the remaining 2 here. And the third case is I will keep 1 molecule here, 1 molecule here, and then 2 molecules here. And then the fourth case will be I can use 2 molecules here, 1 molecule here, 1 molecule here. Okay, I mean think I am sounding correct only. That there will be total 6 microstates as sir explained. Macrostates. It will be macro. So how many we got? 1, 2, 3, 4. So we need to find out the remaining 2. Which one I am missing? So 2, 1, 1, 1, 1, 2, 1. Okay, that is I forgot that. Yeah, we can get this one also. 1, 2, 1. This is one case. And yeah, here also we will get 1, 3. So first case, second case, third case, fourth case, fifth case, sixth case. Okay, we have total 6 microstates. So if I ask you to find out the how many configurations, we can fill it here. Say suppose if I ask you to find out this one, so it is basically example of 2 comma 1 comma 1. In this configuration, how many microstates we can attain? So this will be simple as 4CT. So you have two molecules, you can take into 2C1, you can take only one molecule into 1. So it will be 4 factorial by 2 factorial into 2 factorial. It will be 2 factorial into 2 factorial into 2, 1 factorial into 1 factorial into 1. So it will be 4 into 3 divided by 2. So it will be 6 into 2, 12. So any doubts in this? So once this is done, so it's the same we can find it for the others also. Suppose if I take the 1 comma 3 this condition, the fifth case, so it will be 1 comma 2 comma 1. So here also same, it will be, you need to keep one molecule 4C1, and then you will remember the 3C2, and then you have one molecule left. So it will be 4 factorial divided by 3 factorial into 1 factorial into 3 factorial divided by 2 factorial into 1 factorial into 1 factorial. So it will be 4, because into 3 factorial it will get cancelled, into 3 because you will get 12. So you need to understand that whatever you are doing, you should remember this. So then we will take this first case, which is 1 comma 3. So what we will do is, so first we need to get one molecule 4C1. So I mean out of 4 we need to pick one molecule, and the remaining 3 will go here. So it will be only one chances. So here how many chances we will have? 4 chances. Okay, so if you take any two cases condition, say suppose if you take this one also, 2 comma 1 condition, 2 comma 1 condition. So here also you need two molecules. Sorry, I think 1 comma 3. 1 comma 3. This is for the first macrostate, and this is for the last sixth macrostate. So here also we will get the 4 cases, 4 macrostates. So you can understand that the what do you call, if you are doing any mathematical or statistical problems, you will see that okay, how the error bar is averaged over the, say suppose this is the curve, we will see that how the error bar is averaged over the graph. Okay, so if you see, if the 1 3 is there, or say suppose this cases, the values of microstates you will get are only 4. Okay, it means you can distribute the graph in only 4 ways. But if you take the cases of like this, when the molecules are randomly distributed, I mean the molecules are distributed in more states, more energy states, you will get the number of microstates. So this will called as thermodynamic probability, which is feasible thermodynamic probability. So if you ask me, the most feasible thermodynamic microstates will be this one, and this one, and this one, compared to these two. So that's like from there we can get the equation, derivation of thermodynamic probability. So what does thermodynamic probability says? So what does it says was the number of systems microsystem corresponding to given macrostate is called so basically it's nothing but these values. These are called a thermodynamic probability. So this is nothing but n factorial by n1. 1 second. Yeah. So this is nothing but So if I, so it's nothing but you can say if I write as NCA. So basically it is nothing but same thing like this. So that's what we did it here. And the most feasible one, the most feasible macro state is the one having maximum number of microstates, that is having the most disorderly order. So if you, so yeah, if you take this one, if you have them in the more disordered system, so suppose if you have the more, so one here, two molecules here, one molecule here, it will be more disorder, and when calculating the partition function also, it will be, the values will be so accurate compared to if you do like this, compared to this one. Sorry, the example will be 6 right now. So yeah, if you take this example and if you put here one, so yeah, if you take these two example, there will be more sparsity here compared to here. That's what we are talking here. Now we will derive the thermodynamic probability. So now we are going to derive the thermodynamic probability. So I will go with the, one second. Yeah. Just want to see. Okay, fine. Is that just, you can see the screen, right?
Yes, sir.
Okay, fine. Thanks. So in thermodynamic probability, we are just, I'm just writing this. I'm just going to give the brief theory of what SAR says, because you need to remember this theory. I mean, if you remember these formulas, not the formulas, the thermodynamic potential and the partition function and all the things. So while in the future, if you are studying about any biological systems, so everything starts from the formula of e power minus E by kt divided by sigma of e power minus. So this will be the basic formula in the future. I mean, if you come to the research side, if you want to study, okay, how far the drug is moving, how the protein is interacting, and everything, the partition function is the main thing. So you need to understand it better way, so that in the future, the whole classes from here only it will take the what do you call. In the research point of also, if you want to develop any new theory, also it derives from this equation, the basic equation. So now we know that W equal to n factorial by n1 factorial, n2 factorial, n3 factorial, and so on. So now if I can write it as W equal to n factorial into, so pi is nothing but the multiplier. So here if I apply the ln of W equal to ln of n factorial minus ln of pi I ni factorial. So it will come as, so it is ln, it will come as ln n1, ln of n1 into n2 into n3 into and so on. So it will become as ln n1 plus ln n2 plus and so on. So it is nothing but, it's better to write like this. So you have this equation. So from Stirling approximation, we have the function of, so if you use the same formula on here, it will be n ln n minus ln n minus, I'll give the sigma as it is. Okay, so this is the equation which you will get. Sorry, my mistake. That's what I'm thinking, it's a very mistake. So we have it here in Ni, right? If you remember this formula, I rewrite the formula here. Ln n factorial minus sigma of ln ni factorial. So from Stirling approximation we have this formula. So if you write it this formula here, we will have, sorry, equal to n ln minus n minus sigma of ni ln ni minus ni. So if I fulfill it, this will become as so we know that nothing n is nothing but sigma of total n. So this will get cancelled. So we'll end up with so now I am differentiating this equation because to get the equilibrium condition, this is the equilibrium condition. Because as you all know that thermodynamic probability we have the different macro states and what is this example here? Yeah. See, I said that this is the most feasible one, but we cannot distributing that how many there are 12 microstates and there will be molecules moving up and down. So that's why it won't be it won't be constant until unless it kept it in the equilibrium. So to get that you need differentiating with you are differentiating it to 0, then only it can become as maximum. So if you do this, so we got d of n ln n minus sigma n ln I. So now so you apply the UV rule. If you apply the UV rule, so then it will become as n ln n I will take the sigma out. So now we have yeah. So now we have this one as n into n by n into dn plus ln n dn minus this one minus sigma ni d of ln ni minus sigma of ln ni dni. So from this equation what we can get was ln n dn plus dn. So this dn I am writing the next and I am keeping it here. So we will get so dn will get cancelled because it is constant and this is will get cancelled because number of particles are constant, right, always. So now again this is also will get cancelled because we will get ni. So the final equation is sigma ln ni dni equal to 0. Okay, because here the number of molecules are not number of particles or molecules are not constant. So that's why this won't get that's why this is not this constant is this derivative is not 0, remaining all get 0. So this is at the end we will get the formula. So still we are not get any conclusion. So from this we will apply the Lagrange equation, Lagrange undetermined multiplier. So to get it into the one form of, like, say suppose what we have done was we need to find out the number of particles in that microstate. So we need to do what is the energy for that ith state. So that's why we are doing this. So what the Lagrange tell was, if you do this equation with two constants with assumption 1 plus with assumption 2 equal to 0, then we can easily able to solve this. So what are the two assumptions which we can take it from here was, we know that n equal to sigma ni and dn equal to 0, and we know that e equal to sigma ni ei, where de equal to 0. So we are taking these two assumptions. So we are taking to this assumption and we are keeping it with alpha and beta. So then we will get the equation like this. So alpha dni plus so now if I take dni common, so we know that we already said that dni is not equal to 0. This is not equal to 0. So then this will be equal to 0. So then ni will be nothing but e to the power minus 8 into e to the power of minus beta gamma I. So now we know that n is nothing but sigma ni. So which we got sigma of e power minus alpha into e power minus beta sigma of I. So now for to get the e power alpha is constant here. Yeah, e power alpha is constant. So if I get it from here, e power minus alpha equals to n divided by sigma of e power minus beta, this one. So I'll keep this equation in this. So we get so the relation between the number of particles in ith state versus the energy. So now if I keep it as n by n equal to so this will give the probability relation. So how many molecules can be in ith state with respect to the energy state equation. So this is the one basic equation. So but still we don't have the value of beta here. So to get the beta value, so what we will do was, we will take this equation and we will give the partition function q as sigma of 6. So now we know that n by n equals to e power minus beta epsilon by sigma which is nothing but ni by n equals to. So now if I apply the ln on all sides, so it will be so this will go like n into e power minus beta q. So ln ni equals to ln n plus of minus beta e. Now it will be minus, so ln q. So that's what we are written here. So now we have this equation, and then from here keep this equation, and then so we have the third assumption, which is Boltzmann-Planck entropy assumption. So in the statistical mechanics, this is how we define the entropy. This is the Boltzmann constant. We will discuss more about this in the future classes, or how the entropy is related to the thermodynamic probability and the Boltzmann constant. So for now, just remember this formula: S equal to K into ln W, and we have ln Ni this, and we know the ln W as S by K equal to ln W, and we know S by K equals to ln N minus of sigma A. So this we are getting from here. If you remember this one, this equation, I am using it here. So now we have this equation, and then now in the last slide we got the B equation, where we can apply this ln Ni here. So it will be ln N minus beta sigma I minus ln Q. So now if I expand the equation, we get ln Ni minus, so it will be sigma Ni ln N, so it will be nothing but sigma Ni is nothing but N, so this will be N ln N. Then again we have sigma of, we get sigma Ni beta epsilon I minus, we get again, so we get minus minus plus, so we get this plus sigma Ni ln Q. So this will get cancelled. So now we have the equation of this is counted as N, and here also we are writing this as N. So now we have N beta I, sorry, I made the mistake. So what I am doing was, so I am writing this as N ln N, so I have written, yeah. So now what I am doing was, here we have the sigma I Ni epsilon I into beta, so plus sigma Ni ln Q. So we know this is the total energy, and this is the only N equal to sigma Ni. So now the S by K will be equals to this will get cancelled. So now it will be E beta plus N ln Q. Okay, so now what we can do it was, so this is the equation which we have now. So now these are the two terms which we have here, which are not constant, which can change with the systems. That is, one is entropy, another one is energy. Remaining all are the constant terms, and the Q also. So now what I will do was, I will do ds by dE at constant volume will be equals to, I'm just writing the first equation, then I will explain you. dE plus beta k plus k. I will explain this equation again, 1 minute. So it will be nk by q into dq by d beta into d beta by dE plus k beta plus k d beta by dE at the constant value. So how we got this equation was, so basically what I done was, so we have, what are the properties which we are changing with the states was, one is entropy, one is overall energy, another one is ln Q. Ln Q is nothing but, Q is nothing but, Q is nothing but sigma of e power minus. So here also we have the energy term of the particular ith state. So what we will do was, so we will ds by dE, so because this is the total energy, ds by dE equals to, I send this k here, so now we have the ke beta plus nk ln Q. So now the nk is there, d of ln Q is nothing but, d of ln Q is nothing but 1 by q dq. So now this dq will be divided by de. So that's what we are written here. Now we know that q is nothing but the function of the beta and e. So now we have derived this one as chain rule. So what we done was, okay, so this is what we have done. We have rewrite it. So then we have ke beta. So now we already know that k is constant, so we kept e beta 2 times. So we are doing for the e beta to here we have the ke beta. So we have the ke beta. If I apply d by de, we know that k is constant, so it will be of, so it will be k beta plus, so that's what I written here. So I written in one sentence the whole formula, which has, so this is the final equation which we got. From here what I will do was, so I will do this one also, q equal to minus e power, so now they said dq by dt. So now if you do dq by d beta, so this will come as minus, this will come down, so this will become as minus e, so sigma of minus ei. So this will be the equation. Now I am doing ni by ni, total number, so it will be minus n sigma ei by e power minus beta ei divided by n. So now I am writing the ni as sigma of ni ei e power minus beta ei by n. So this is nothing but energy, so this term will become as minus e by n into, this is nothing but the q again, q. So now this will become as nq by q into minus e by n into q to plus so now the final equation, which now if you assume that the total energy is nothing but the total internal energy, so then you get the formula of k beta. So now from the thermodynamic properties, we know that ds by du, if you see the Lagrange transforms, we got this, so which means 1 by t equal to k beta, so beta equal to 1 by kt. So now we will keep this beta in the minus e by kt divided by, so any doubts in this equation? If you have any doubts in any step, I will explain it again. Just let me know if you have any doubts how we got this equation.
No, sir.
Yeah, fine, thank you. So now after this, what we have is partition functions. So now what, from the starting of the class, what we have discussed was statistical thermodynamics, and then once we have discussed statistical thermodynamics, we have discussed that what is thermodynamic probability. Once we have discussed the thermodynamic probability, and then where we got the equation of number of particles in ith state versus this equation, and then now we don't know the what is beta, so then we solved the beta equation using the Boltzmann Planck constant, where we got beta as 1 by kt. Okay, so as of now we have discussed these 4 topics, just to give the outlet of what we have discussed. Now we have the partition, sorry, we have already discussed the what is partition function, so this we call it as partition function. So from here, how can we use the partition function with thermodynamic properties? So for this what we can do was, so we know that e to the power minus, I will write the beta first. This is the formula, so which is nothing but by kt. So now if I am writing the internal energy, so it's nothing but E it is nothing but so Ni from here we can get it as N by Q into e power minus beta of E. So Ui is nothing but, so see how we are connecting the microscopic, we know the microscopic properties, like say suppose microscopic particles. Okay, we have how many particles and this ith state, and then we can directly conclude the microscopic property. So this is the relation. Basically what we are doing was, so we know the macroscopic, how can we calculate the U in terms of delta U, but here we are calculating the U, the overall properties. So once you have U, and then we can have the, one second, just you can go for the S also. S as function of Q, so you know that S equal to K into ln W. So now S equal to, which we have done it here, this one, S by K equal to E beta. Now I am using this formula, so I am using this X formula. So from X we know that X by K equal to E beta plus N ln Q, which says S equal to K E beta plus Nk ln Q. Now we can write beta as 1 by kt, so then kk will get cancelled. So we have E by T plus Nk ln Q. So now we know that K is nothing but U ln Q. So you can take the U formula from here, then again you can keep it here, so you will get the same thing. Yeah, I think yes. So this is for the S, and if I am talking about the P, so from the thermodynamic properties, again you need to go to the Lagrange series. We know that P equal to minus dA by dV at constant T. Okay, now we need to know what is A. A is nothing but U minus Ts, Helmholtz energy. So which is nothing but A equal to U minus T into N K ln Q plus U by T. So this T will get cancelled. T and K ln Q minus U. So now A equal to minus NTK ln Q. So now we will put it here. So now the P will be, so here minus is there, here minus is there, so it will become as NTK ln Q by dV, because this is the only term at constant temperature, this is constant, so this is only the changing term. So this is how we can get it from the microstate to the macro state, I mean from the partition function. You can try other examples also, how can we go from the one state to another state. So once this is done, what we have is monatomic gases. I will go very fast in the monatomic gases, because what we need to understand from the monoatomic gases is, so we have the monoatomic gases, where we are considering only translational. We are not considering any rotational vibrational. Translation means it's just the molecule is moving, it's not, say suppose translational. We have different types, there is rotational also and there is vibrational. if you take one particle, it is just moving from one direction to after certain time it will goes to here. This is called a translational. So suppose it is going like this, I mean it is rotating like this, and it gone to here, that is called as rotational with a translation. And then there is a vibration, like it is vibrating by itself, like I'm just giving the example like how it works. So it will go like this. So here there is a translational as it moves from one point to another, from here to here, and there is rotational, it is rotating, and there is vibration also. So but consider a case where there is only one property which is translational, which means the molecule is like it's like you are moving one object from one position to another position without changing its rotation or without changing its vibration. So that is called as translational. So where we have the energy under the partition functions. Now from Schrodinger we got Schrodinger. From Schrodinger we got energy as n square h square by 8 ma square. So here n is quantum number integer. So in the future classes I will get you this derivation. Okay, as of now I know that the Schrodinger equation deals with the x, y, z and time with the potential energy function, with potential energy function of v of x comma y comma z, and I will get you from how this equation from so this equation gives to this. I will come it in the next classes, so I am also reading about it, so I will let you know once I get the information about this. So now assume that we are taking at only one direction. Say suppose the molecule in the box, we have the box, cubic box, where the confined space it can go in x direction or y direction or z direction. Assume it is going in only one directional translation. So then we got q trans equal to, so this is the equation, and then we know that E energy is nothing but q trans equal to sigma of e to minus beta h square n square by 8m a square. This is for the one dimension. If we are taking the 3 dimension, then it will go as q trans 3d equals to sigma n equal to 1 to infinity e to the power minus beta. So 3 dimensions. So then for the sake of simplicity in mathematics, so we are keeping 0 to 1. So we know that 0 is nothing but it will be 0. So e power 0 is nothing but 1. So we are subtracting that term here. Okay, so this number will be very huge compared to this, so that's why this will be eliminated. So suppose if you take this much big number, so it's nothing but, so that's why we are eliminating this one. So why we have done this step is to get from the 0 to infinity, so that we can integrate this term. Square whole cube. So now if I integrate from 0 to infinity to reduce the space, so it will be dn cube with respect to dn. So this, if you have the formula of e to the power minus, say suppose bn square dn, say suppose if you have e to n square equal to x, then 2n dn equal to dx, then dn equal to dx by 2n. It's nothing but half into, now n is nothing but x to the power 1 by 2. So now you got dx, the dn term. So now by applying this rule, so now this whole will become as this will become as, if if I apply integral 0 to infinity here, so this will become as half into integral of e to the power minus x into the x to the power of minus 1 by 2 dx. For this, in the mathematics integration, there is a standard formula of which is nothing but square root of pi by b. So for this, if I do this equation entirely, so I mean this equation, why I am explaining it was very fast. So where we are going, I will let you know. So this is nothing but pi. So b is nothing but, here we have the b is this one. So that we need to keep it here. So it will be 8ma square divided by beta h square to the power 3. So this, the final equation will be q equal to v by lambda cube. So because we are taking the acceleration out, acceleration is nothing but velocity. We are doing it, area square is nothing but the velocity, volume. So it is volume, you should remember it is volume, not velocity, sorry. Here it is a square is area, so area square is nothing but the volume, area cube. Area in 3 directions is nothing but the volume. So the units of lambda will be in the picometer. So now the lambda cube is nothing but h square. So this is in the class also it is there. Why we need to go through this was, I will explain you in 1 minute. So we get this formula for the partition function. So basically from this function, this formula we have gotten into this. Okay, so why we have gotten into this was, if you know the, just give me 1 more minute, I will explain it. So now we have q as v by lambda cube, where lambda equals to h square by 2 pi m kt whole to the power 3 by 2. Now if I am taking the different thermodynamic components, thermodynamic quantities, say suppose I want to figure out the whole energy. So we know E equal to sigma ni ei. Bear with me for 2 minutes, I will explain you why we are where we are going. So now this equation will go as n by q into e to the power minus beta e1. So the now u equal to n by q is constant. So now sigma of ei minus e to the power minus beta ei. So now we are getting, if I apply the dq by dt here, so you can take this formula also. So what I am doing was, so I am taking E equal to minus n by q d ln q by d beta. So now if I do this, if I keep ln q this value, everything, so then E will become as minus 3 by 2 n of do beta by ln of 1 by beta. So now this whole equation will become as, so ln of 1 beta by is nothing but 1 by beta square. So we will get the cancel, and the minus minus will get cancelled. So the E by 3 to n kt. Yeah. So just for this derivation, you can get it in the SAR notes also. If you are not understanding the derivation, just mail me. In the next class, I will explain it clearly. So why I am coming to these two equations was, so in the, where you are talking about the classical thermodynamics, we say that there are two types of properties. One is extensive and one is intensive. Intensive is the one which won't change with the system's change. Suppose if we are adding x number of molecules, if we add x number of molecules, the density won't change. Or if you increase the volume also, the density won't change. But the extensive is like entropy, the temperature and all the things. When you increase the temperature, the system will get double. Say suppose if you are increasing the volume to 2 volume, number of particles to 2n, From the classical thermodynamics it should be 2s, but what we are getting was from the Gibbs paradox. So we also know that this formula is, you should know this one, S equal to, so this is from this one, nk ln q, assume that y, so I'm writing the y formula here. So now if I made these conditions here, so now I am rewriting the equation with the terms of which we know from the here the E and the Q formulas. So from here we can understand that nk ln of 2 pi m kt by h square whole to the power 3 by 2 into v plus 3 by 2 nk t by t, so tt will get cancelled. So now we have the formula of, so this is all there in the SAR class, so I'm just rephrasing the words what SAR has ended with. So this is for the monoatomic gases. Now if you take this condition, what I can do was the new entropy will be, say suppose the volume will be 2v, so here it will be 2v, so here it will be like to put it in the good words, we can write this equation again, s dash equal to, so whole equation I'm not changing anything, I'm just rewriting the equation. So I'm increase the number of molecules to 2n, I'm doing this, that's it, 2n kt into ln of 2 pi m kt by h square whole to the power 3 by 2 plus into, here we have v which I am converting into the 2v, plus again we have 3 by 2 into 2nk. See, if you see the formula of this one, if I increase n to 2n, this will become as E equal to 3 by 2 into 2n kt, so which is nothing but 3 by 2 n kt, which is nothing but 2 E initial. So the internal energy is expanding in terms of the extensive property, so that's we want to check it for the entropy also. So here we have 2 nkt, this one and all, so now the ln is there entirely. So now what I will do is I will separate it. So now if I separate it, we got ln of plus again we will get the same thing, so which is into 2v is there, right? Yeah, into v plus 2 nkt ln 2, I'm divided this 2v into 2 into v, so now we have ln of, here it is ln of, this is a, 2 as b, v as c, so now I have taken ln av into b, so now it will be ln av plus ln b, so now I have taken this all into together and 2 nkt ln 2 separately, plus we have two types of E initial. So now the snk will be like this is same, if I take 2 common out of this, which is not equal to 2s, so this is nothing but SAR says as Gibbs paradox. So what from the statistical mechanics, whatever the assumptions we have taken from the thermodynamic probability while solving all the equations from the say suppose after considering the thermodynamic probability and after considering the partition function and everything, at the end we have attained to the value of that entropy is not becoming as extensive property with compared to the classical thermodynamics. So it means the assumptions which we have carried out for the first initially were wrong, and we need to change the assumptions of thermodynamic probability. So that we will study in the next class, and I think Vishwajit is there. So I have bought. If you have any questions, you can ask me. Otherwise, we will solve this sample 2 questions. Hello.
Yes, sir.
Yeah. So can you solve this question, Viswajit? So before understanding that, if you understand today's class, so we have started initially with. Okay, you can give a try for 2 minutes. I will explain you after 2 minutes. So can I explain? So have you got the answer?
Yes, sir.
Okay, fine. So can you tell me answer for the first question? Wait, let me try. So we have 6 particles, out of which 2 are restricted and 2 restricted. So we need to keep 2 in the one. Can you give me the answer for the first question? So the combination formula will work for the microstates, okay? For the macrostates, you need to go like in the question they ask for the microstates, right? So there are 6 particles. There should be restricted 2 energies. So it means you can have 3, 3, 3, or say 4, 2, or 2, 4, or 1, 5, or 5, 1. Is there any other option? 3, 2. Sorry, 3, 3 over. Vishwajit, is there any other option you got? How many? What is the answer you got?
So 5.
5, yeah. So 1, 2, 3, 4, 5. So you are the same way, right?
Yes, sir.
So now the given question, second question was, so in the second question they asked that what would be the number of microstates corresponding to the macro state 1 comma 5. So there are, where is this? So yeah, 1 comma 5 is this one. So the ground state is 1, the upper state is 5. So can you give me answer for this question?
6.
Yeah. So I mean this will be helpful for, this is the last year's question. So we'll get the same question, I mean same modular question in this experiment also. So now can you give me this one? So basically this type of question what they are asking was, so once there is thermodynamic probability, what do you mean by thermodynamic probability is nothing but microstates given by the macro state. Okay, so it means you need to find the microstates again. So you can use the formula to find out. So can you tell me the answer? So first we will calculate thermodynamic probability. So there are total how many states? First state, second, third, fourth, fifth, sixth, 7 states. How many molecules are there? 1, 2, 3. So 7 factorial by 4 factorial into 3 factorial. 7 into 5 into 6 by. Have you understood the concept?
No, sir.
So basically, when thermodynamic probability is asked, so what does it says was, first of all, this question. Okay, so what does this question says was the molecule X can move between and occupy any box. So and they are asking that if we say if we give the thermodynamic probability definition, the definition states that number of microstates corresponding to given microstate. Okay, so for initial, forget about this formula. Okay, this formula is already known, right? Okay, for a few minutes we'll come to the definition of the thermodynamic probability. So what the thermodynamic probability says was number of microstates corresponding to the given macrostate. Okay, they given one macrostate, so this is macrostate where they have 7 states. So suppose assume it has 7 energies, 0 1 2 3 4 5 6 7, and they said that the molecules are at this level, say suppose 0th level, and there is third molecule here, and the molecule is on the 5th state, and they are saying that the molecule can move to any state. So now to understand that, so totally we have the 7 states divided by how many it can occupy is any 3, right? It's not that only this 3, it can occupy this one and this one and this one. This is also one microstate. You understand, right, my problem, what I'm saying?
Yes, sir.
So now we have 4 divided by, so they given one macro state saying that from here they are asking that calculate thermodynamic probability. From the definition of thermodynamic probability, you should understand that number of microstates corresponding to the given macrostate. So macrostate is this, and there are total 7 boxes, and there are 3 molecules, and the 3 molecules can be fit anywhere. So how many macrostates you can get? Microstates. So that is, and if you see the thermodynamic probability is nothing but the maximum occurrence of microstate. So now the answer is 35. You remember, right, how to solve this type of questions? And can you tell me
Yes, sir.
can you tell me the entropy? Here they ask the entropy also. So you remember this formula from the Boltzmann-Planck constant, so which we discussed, I'm not wrong. So at the equilibrium condition, so I think we have discussed somewhere the Boltzmann constant. Not here. 1 second. Yeah, see here. So from this we have derived the function, right? S by k equal to ln w, and then we have got the what do you call this equation? E equals to this one. Which one you got? Yeah, u equal to u, and then we got this whole equation, right? So where you got E equal to minus E by n cube. I think this is the formula, right? Sorry, this is for Q. This is wrong. So you remember, right, why we are using the thermodynamic potential? Sorry, entropy. So you have seen this formula in the class or recent. You can revisit the video why we are using this, how we got this Boltzmann constant relationship. Hello.
Yes, sir.
Yeah, have you known this equation, right? S equal to k into ln w.
Yeah.
Yeah, so from that equation you can calculate the, so you know that w is 35, the ln w is 35, so you know the value of ln 35 into kb. So if it is asking the Boltzmann constant with the values, then you can give the values. And I think for the assignment every question has been given with the desired I mean I have explained all things, the equilibrium conditions and the entropy functions and the how to solve this type of questions and all. If you have any doubts, you can ask.
No, sir.
Vishwajit, I mean, I can ask you a question like, where are you from? I mean, which college? Just for the interaction purpose.
Um, I have completed my college.
Okay.
I've done MSc Biotech. Currently, I'm faculty at
Engineering college.
Aditya Agricultural Biotechnology College,
In
Bid.
which, I mean, place?
Bid. Maharashtra.
Acha, acha, Maharashtra. Okay, okay, fine. So you have any doubts in the classical and statistical?
Uh, what's up?
I mean, if you have any doubts, you can mail me. I mean, before the class, so that I can. I will also be prepared for that class. Okay.
Okay.
Okay. Thank you for your
I mean, if there will be any doubt, I'll post it on
discussion
Google for
forums. Yes, yeah,
yeah,
discussion forum. Then I will explain it in the class. And yeah, thank you, Vishwajit, for attending the class.
okay.
Thank you.
Okay, sir.
You can leave. You can leave.
Okay, thank you.
Thank you, Vishwajit.